Hello again, and welcome to the next video in week 4 of Reigate College's post-Easter work for maths. This video, we're going to be looking at improper fractions using algebra and how those link with content you've done already, specifically partial fractions. But the first thing to kind of think about is a reminder of what an improper fraction is. So let's look at this in terms of numbers. An improper fraction is a top-heavy fraction. This is improper. Now, obviously, for a lot of numeracy and maths that we do, this is a really useful way to write a fraction. But we can also write it in a different way, as a whole number and a fraction. What do these numbers represent? So this is how many times 3 goes into 8 completely. Okay. And this is what's left over, which we know is called the remainder. And notice the denominator of this fraction is the same as the denominator of this fraction. Now, the other way we can express this, if we rearrange, we could say that this is the same as 2 plus 2/3. So 8 over 3 is 2 plus 2/3, which means that we can write 8 as 2 times 3 plus 2. Now, this may not seem particularly sensible to do that, but it's very useful to think about things in this way if we look at things with fractions, particularly algebra. So, what is an algebraic improper fraction? So this harks back to the end of the last video. An improper fraction, or an algebraic fraction, is improper as if the order of the numerator is bigger than or the same as the order of the denominator. For instance, x plus 1 over x minus 1. The order on the top is 1, the order on the bottom is 1. It's the same. We could have x to the 4 plus 3x squared minus 7 over x squared plus x plus 1. The order on the top is bigger than the order on the bottom. It is improper. Now, we want to generally be able to split these up. A lot of what we'll do with this next year is do integration and differentiation, well, specifically integration with this kind of thing. Which, if we leave our answer like this, is very, very difficult to do. What we want to do is be able to split this up into lots of different bits. Because if we can do that, we can then integrate each of the little bits and then add it all together. So, let's say we've got some function over a different function. Okay, so we have some function and a divisor. We know that that can be written as something plus a remainder. Over g of x. So any function can be written as another function times a divisor plus a remainder. Now, what q of x and f of x are will vary depending on the question, and really everything will change. So let's have a look at an example, because talking about this in words is a little confusing. Let's have a look at question 1 on page 24 of the workbook, which looks like this. Given that x cubed plus x squared minus 7 over x minus 3 equals ax squared plus bx plus c plus d over x minus 3, find a, b, c, and d. So, going back to our previous example using numbers, we can see we've got something that looks like this. A fraction equals some stuff plus another fraction. Granted, it doesn't look a lot like this, but we can still think about it as an improper fraction. So this is our improper fraction here, is equal to some function plus a fraction. Now, there are lots of different ways that you can approach this question. You can work this like we do with partial fractions, where you multiply through by x minus 3, compare coefficients, and solve a bunch of simultaneous equations. That will work fine. What I tend to do is something that you have already done, is algebraic long division. We are doing x cubed plus x squared plus 0x. I put that in to make sure things stay in the right columns. And we are dividing that by x minus 3. Remember, what goes on the top is how many times this goes into this function completely. So what goes on the top is going to be exactly this. What we'll be left with is a number at the end. That's the remainder, which will be d. So when we did algebraic long division before, we looked at the factor theorem, and we found the remainder was 0. Because it went into, one function went into something else exactly a certain number of times. There was nothing left over. So let's look at this now. So how many times does x go into x cubed? Well, it goes in x squared times. We multiply down, and we subtract. X squared minus 3x squared is 4x squared. How many times does x go into 4x squared? Goes in 4x times. Multiply down. And subtract. How many times does x go into 12x? Well, that's 12 times. You multiply down. Minus 36. And we subtract. Minus 7 minus 36 is 29. Which tells us that x cubed plus x squared minus 7 over x minus 3 is equal to the function that we have plus our remainder over the divisor. So comparing that with the form that we want to get to, you can see hopefully we've got there. So therefore A is 1, B is 4, C is 12, and D is 29. As I said, you could do this by using methods that we have already looked at with partial fractions. Multiplying this through by x minus 3 and then putting in values of x. Or multiplying it through by x minus 3, multiplying it out and comparing coefficients. I generally find this is quicker. And often this is what the exam board will expect you to be doing. Now, they could ask this question in a different way. They could say, given that x cubed plus x squared minus 7 is equal to ax squared plus bx plus c times x minus 3 plus d, find the values of a, b, and c, and d. And this would be exactly the same question, it's just rearranged slightly. So if you get this kind of thing, again, this kind of leads you towards the more partial fractions kind of way of doing it, of multiplying out and comparing coefficients, or sticking in values of x and seeing what happens. But you could still do it the way I've just done, the same example written in a different form. So don't panic if this kind of thing comes up. So before we move on and look at linking this with partial fractions, I want you to practice this a little bit more. Okay, so exercise 1F, page 16, questions 1, 4, and 5, and then if you feel like a challenge, have a go at question 10 as well. Now, when we come back, what we'll do is we will look at the second example in the workbook and then extend it slightly. Okay? So pause the video and then come back and we'll have a look at question 2. Okay, so coming back to the workbook, I'm just changing it slightly here for the purposes of this because I'm going to add a part B that's not there. Part A will do exactly as question 2 is saying there. Part B, I will add a little bit on the end. So part A is effectively exactly what we just did. Okay, we've got a fraction, and then we've got not a fraction plus a little bit left over. The key difference here is that our remainder is going to be algebraic. Whereas in the previous example, the remainder wasn't. So, how do we know this is going to look like that? Strictly speaking, with question 1, if we weren't told, scratch that. So it's to do with what the denominator is. This, when we are writing out the general form, must be order less than the denominator, or 1 less. So the denominator is quadratic. This has to be linear. The general form of a linear equation is mx plus c. So we've just used different letters. If this was cubic, it would have to look like ax squared plus bx plus c on the top. It's always 1 less. It's not generally something you do have to worry about for the maths A level. Further maths is a little bit different, but we'll see that this works in exactly the same way. So let's start with, we've got x squared plus 2x minus 3 is going into x to the 4 plus x cubed plus no x squareds plus x minus 10. So Like before, we look at the first term here and the first term here, and then everything else kind of falls into place. So how many times does x squared go into x to the 4? It goes in x squared times. We multiply down. And we subtract. So x cubed minus 2x cubed, we get minus x cubed. 0x squared minus 3x squared is plus 3x squared. And then plus x minus 10. So x squared into minus x cubed goes minus x times. And we subtract. 3 minus minus 2 gives us 5x squared. X minus 3x gives us minus 2x. And then we've got the minus 10. X squared into 5x squared is 5. Multiply down. And subtract. So we've got minus 12x plus 5. So therefore, A is 1, B is minus 1, C is 5, D is minus 12, E is 5. Okay, so x to the 4 plus x cubed plus x minus 10 over x squared plus 2x minus 3 is equal to x squared minus x plus 5 plus minus 12x plus 5 over x squared plus 2x minus 3. So A is 1, B is minus 1, C is 5, D is minus 12, and E is 5. So here comes my part B, which if you've printed off the workbook page, unfortunately you won't have enough space for, but there we go. Hence, express x to the 4 plus x cubed plus x minus 10 over x squared plus 2x minus 3 in a form involving partial fractions. So linking what you're doing now with what we did in the previous video. Now from part A, we know that this fraction is equal to x squared minus x plus 5 plus minus 12x plus 5 over x squared plus 2x minus 3. So this is the bit we need to worry about. This is the bit that we need to use our partial fractions method on, because that's not partial fractions. We can see this bit is fine. There's nothing wrong with that. That just is there. That's as simple as it gets. This we need to simplify further. So we can say let 5 minus 12x, just writing it round so it's tidier, over. Now, because of the way partial fractions works, we know we need to factorize the denominator. And this one conveniently does factorize to x plus 3, x minus 1. So we know this is going to be something over x plus 3 plus something over x minus 1. Now, what letters should we use? Strictly speaking, we shouldn't use A, B, C, D, or E, because we've used them in the previous part of the question. And do be very careful with this. Sometimes, when you are doing this type of question in the exam, they will jump straight to this part. They won't do the part A. So you need to be very careful with your labels not to use the same letters twice. Specifically, use the letters you're told. I'm going to use P and Q because why not? So from here, it's just a case of doing our normal partial fraction stuff. Okay, multiplying through by the denominator, and then choosing some numbers. Now in this case, we're not going to get nice partial fractions, but this still makes the point about them, about how you can link what we're doing here with partial fractions. So when x is 1, this side is minus 7, this is 0, and we get 4q. So q is minus 7 over 4. Again, not particularly nice. Typically not going to happen, but if it does, it does, and that's just the way it goes. So if we let x is minus 3, we get 5 minus 36, which is 41, which already tells us it's not going to be a particularly nice number because this is prime, is equal to minus 4p. P is minus 41 over 4. So we know that this can be written using these. Not very nice, but again, oh well. So therefore, x to the 4 plus x cubed plus x minus 10 over x squared plus 2x minus 3 is equal to x squared minus x plus 5 minus p. So 41 over 4 x plus 3 minus q. And this is how you deal with if you get fractions while doing partial fractions. Obviously, it depends on the wording of the question, but there we go. So to practice doing this with partial fractions, what I'd like you to do is exercise 1G, page 18, questions 1, 3, and 4. And again, if you want a challenge, have a go at question 9. The next video will move away from fractions and look at the last form of proof for the Maths A-level, which is something called proof by contradiction. So, something to look forward to. Thank you.